we talk about these different molecular structures, we also need to take into consideration the kind of bonding that we're seeing. And so right now I'm going to distinguish sigma versus pi bonding for you. So first off, let's start out with sigma bonding. This is when two orbitals, each with one electron, overlap or interact with one another. So in this case, we have two s orbitals interacting to create a sigma bond. Here we have a sigma bond with two p orbitals, and this is called end-to-end overlap. And again, this forms one sigma bond. And sigma bonds allow bound atoms to rotate. As you can see, there's a bond axis right here, and you can rotate it around it. And the resulting sigma bond has an electron density with cylindrical symmetry around the internuclear axis. This is the internuclear axis. And so there's a cylindrical symmetry around all sigma bonds. Now moving on to a pi bond. In this case, we have two orbitals, each with one electron that overlap side by side. So pi bonds are only seen for p orbitals, not for s orbitals anymore. And so this is side by side overlap. So pi bonds do not allow bound atoms to rotate, because if you rotate it around the internuclear axis, it's going to break. So bond breaks. This is a very important distinction between sigma bonds and pi bonds. So pi bonds have electron density on each side of the internuclear axis. So when two atoms are bound by more than one covalent bond, the additional orbitals overlap side by side to form pi bonds. So I mentioned this before, but let me do so again. Depending on whether you have a single bond, a double bond, or a triple bond, you're going to have different numbers of sigma and pi bonds. So for everything, you're always going to have one sigma bond. So let me just write that out for each of these. But then for single bonds, it's only a sigma bond. For double bonds, you also have one pi bond. And for triple bonds, you have two pi bonds. So this is a really important table to remember. So as an example, let's look at ethylene. This is a hydrocarbon, C2H4. This first diagram right here shows that there's an end-to-end overlap between the two carbons. This is an sp2-sp2 overlap due to the hybridization, which I'll talk about in a second. But in addition to this end-to-end overlap, which is creating a sigma bond, there's also a side-to-side overlap of these two p orbitals, which creates a pi bond. So this is the side-to-side overlap. And so thus, in order to have this double bond, we have one sigma plus one pi. So what if, on the other hand, you have C, triple bond C, and two H's? So this is C2H2. In this case, let me see if I can draw this out for you in an effective way. We have one sigma bond again, but now we have two pi bonds, right? So in addition to these two side-by-side overlaps, there's going to be another side-by-side overlap, which, let me draw this right here, is going to be this other p orbital. So these two guys are also going to overlap, creating two pi bonds. So for a triple bond, like an ethylene molecule, we're going to have one sigma bond, which is end-to-end, and also two pi bonds, which are the side-to-side overlaps of the p orbitals.